All right. Well, hello, Discrete Math. This is our last section for Chapter 13. So as soon as you're done with this, feel free to work through any of the exercises that are in the book for you. And then tomorrow between 8 a.m. and 4 p.m., I'll have your quiz unlocked if you'd like to take it to see how well you learn the material from this chapter. Our last section, we're going to continue to talk about Fibonacci numbers and the golden ratio. Today we're going to do that within the context of spiral growth in nature. So in nature, where form usually follows a function, the perfect balance of a golden rectangle shows up in spiral growing organisms, often in the form of consecutive Fibonacci numbers. To see how this connection works, consider the following example, which serves as a model for certain natural growth processes. So we're going to talk about stacking squares on Fibonacci rectangles. So to keep it simple, we're just going to start with a 1 by 1 square. We're going to then take that and attach it to a 1 by 1 square. Squares 1 and 2 together form a 1 by 2 Fibonacci rectangle. We will call this the second generation shape. For the third generation, we're now going to tack on a 2 by 2 square. So the third generation is the 3 by 2 Fibonacci rectangle. So now we're going to take that rectangle, which remember had a length of 3, and we're now going to attach a 3 by 3 square, giving us a 3 by 5 Fibonacci rectangle, which we're going to call generation 4. And then by then, you can probably catch on to the pattern. So we started, remember, if you're thinking about just the squares, then we were talking about 1 by 1, then 1 by 1. Here we got up to 2 by 2, 3 by 3. We're now attaching a 5 by 5. And if you notice, just taking a look at one number from each of those squares, or the side length of each of those squares, we're going up 1, 1, 2, 3, 5. I bet you can guess what the next number in the sequence is going to be. Our next square is probably going to be an 8 by 8 square, and that would be how you would continue. So we might imagine these growing Fibonacci rectangles as a living organism. At each step, the organism grows by adding a square, which is, again, very simple, very basic shape. The interesting feature of this growth is that as the Fibonacci rectangles grow larger and larger, they become very, very close to golden rectangles, which is something we talked about in the previous video notes. Essentially, they are all similar to one another. This kind of growth, getting bigger while maintaining the same overall shape, is characteristic of the way that many natural organisms grow. Let's revisit the growth process of that previous example, except now let's create within each of the squares by adding an interior chamber in the form of a quarter circle. So we're going to kind of add in an additional feature. So as we build our squares, we're going to be adding in a quarter circle that's going to connect these two different corners. And again, probably better picture on the following slides, but this gives you kind of the idea of what's going to happen. When you add the next square, again, we're going to continue that, and then we'll be able to see more clearly on the following slides kind of how that's going to work. So like I mentioned, here you are with your first square. You've got your initial growth, then you've got your second square, so now you're continuing that as you add your third square, which again, notice that it's the same shape, it's a similar shape, where you're connecting with a quarter circle, and notice that you're getting kind of this almost kind of, if you think about what's going to happen, is it's going to continue to kind of go up and around. You're going to get kind of this spiral shape to it, which is what you can see on this slide, which is that when you get to 4 and 5, you continue to spiral through those, and then you get to eventually something that looks kind of like this. So the outer spiral formed by the circular arcs is often called a Fibonacci spiral. So that spiral connects back to those Fibonacci numbers that we talked about in the very first notes for this section. So natural organisms obviously grow in essentially two different ways. Humans, most animals, many plants grow following what can informally be described as an all-around growth rule. In this type of growth, all living parts of the organism grow simultaneously, but not necessarily at the same rate. One characteristic of this type of growth is that there is no obvious way to distinguish between the newer and older parts of the organism. In fact, the distinction between new and old parts does not make much sense. I contrast this with the kind of growth exemplified by the shell of a chambered nautilus, or a ram's horn, or a trunk of redwood tree. Those organisms grow following a one-sided or asymmetric growth rule, meaning the organism has a part that's added to it either by its own or outside forces, in such a way that the old organism, together with the added part, form the new organism. At any stage of the growth process, we can see not only the present form, but also the organism's entire past. Something you can't exactly see with a human. You can't exactly look at a human and say, oh, there's the arm from when you were a baby. It grew into its new arm. So very much different from our type of growth. In fact, all the previous stages of growth are the building blocks that make up the present structure. The important aspect of natural growth is the principle of self-similarity, is that organisms like to maintain their overall shape as they grow. This is where nomens come into the picture. For the organism to retain its shape as it grows, the new growth must be a nomen of the entire organism. We call this kind of growth process mnemonic growth. So an example of circular mnemonic growth. We know from our previous section that the nomen to a circular disk is an O-ring, with an inner radius equal to the radius of the circle. We can thus have a circular mnemonic growth by the regular addition of O-rings. You can probably guess what this is looking at. This is looking at a cross-section of a tree where the rings represent each a different nomen. In fact, from what you might remember, if you ever studied environmental science or anything of that sort, is that the number of rings help to tell you the age of the tree. Kind of cool stuff. So O-rings, added one letter at a time, are starting to will start a circular structure and preserve the circular shape throughout the structure's growth. When you carry that into 3 dimensions, this is a good model for the way that the trunk of a redwood tree grows. And this is why we can kind of read the history of a felled redwood tree by studying its rings. Another example of that is a chambered nautilus. So the figure that you see there on the right is a cross-section of the chambered nautilus. The chambered nautilus builds its shell in stages, each time adding another chamber to the already existing shell. And at every stage of its growth, the shape of the chambered nautilus shell remains the same, kind of this beautiful, really distinctive spiral. This is a classic example of mnemonic growth. Each new chamber added to the shell is a nomen of the entire shell. The mnemonic growth of the shell proceeds in essence as follows, starting with its initial shell, which is a very tiny spiral similar in all aspects to the adult spiral shape. The animal then builds a chamber by producing a special secretion around its body that calcifies and hardens. The result then is a slightly enlarged spiral shell, which was similar to the original one. The process then repeats itself over and over in many stages, each one a season in the growth of the animal. Each new chamber adds a nomen to its shell, so the shell grows and it remains similar to itself. This process is a real-life variation of the mathematical spiral building process that we discussed previously. The curve that's generated by the outer edge of a nautilus shell is a cross-section, which is called a logarithmic spiral. More complex examples of this mnemonic growth occur in sunflowers, daisies, pineapples, pine cones, and so on, as I'm sure you remember from our first day when we were looking at those. Here are the rules that govern growth are somewhat more involved, but Fibonacci numbers and the golden ratio once again play a prominent role. All right, guys, that is it for chapter 13. Hopefully you enjoyed learning about some of the cool places that math shows up in nature. Again, if you want to kind of test your knowledge over what we've talked about these last 4 days in the videos, I'll have a quiz unlocked for you tomorrow. It'll be open from 8 a.m. to 4 p.m. And remember, that's just for you to check your own understanding. So don't have to worry about a bad grade on it. Just gives you a chance to check and see how you're doing. Besides that, guys, if you need anything from me, feel free to shoot me an email and I'll get back to you as soon as I can. And I will see you next week to start talking about our next chapter.